I would now like to do an example that illustrates the complexities that can occur with the chain rule. So I'm going to let z be a function of x and y, and then x and y are both going to be functions of t. X is equal to st and y is equal to e to the st. My goal is going to be to take a second derivative of z with respect to time, so I'm going to assume that f has continuous second partial derivatives. So the first thing I'm going to do is just find dx dt. So the derivative of s times t, where t is the variable, is going to be s. And then I'm going to find the derivative dy dt, and that is going to be s e to the st. And now I'd like to find the derivative of z with respect to t in terms of dz dx and dz dy. Okay, so the chain rule tells us that dz dt is going to equal partial z with respect to x times dx dt plus partial z with respect to y times dy dt. Okay, and let's recall here that dz dt is a single variable derivative because we're thinking about z as being a function of x and y, but those are functions of t. Okay, and then I have partials of z with respect to x and y. Those are partial derivatives because z is a function of two variables, x and y. And then I have normal derivatives of x and y with respect to t because those are single variable functions. T is the only variable there. Okay, so I'm going to replace dx dt with s, and that's times dz dx, which I'm going to leave unspecified. And then dy dt is going to be s e to the st. I'm going to replace that with dz dy. So that gives me an expression for dz dt. And now what I'd like to do is move on to a second derivative. Okay, so I want to find d squared z dt squared. Okay, I want to take the derivative of dz dt. So I've copied that expression there. So d squared z dt squared. Okay, that's going to be the time derivative of s times dz dx plus s e to the st times dz dy. Okay, well, that's going to be s times the derivative of dz dx, and then plus, now I'm going to have to use the product rule. Okay, so the product rule says this is going to be s squared e to the st dz dy. Okay, so I'm taking the derivative of the first term and leaving the second one alone, plus s e to the st times the time derivative of dz dy. Okay, so now we're going to have to find that time derivative of dz dx. Okay, so what is the time derivative going to be? Well, we're going to have to take the x derivative of dz dx times, so we'll do that. I'm going to use a bracket here to make it easier. So the x derivative of dz dx times dx dt plus the y derivative of dz dx times dy dt. Now you may say to yourself, why am I doing that? Why am I taking x and y derivatives of dz dx? Well, we can imagine that z, because it's a function of x and y, then dz dx can be a function of x and y. Okay, plus s squared e to the st dz dy plus se to the st times, now I'm going to take the time derivative of dz dy, that's going to be d dx of dz dy plus, or times, dx dt plus the y derivative of dz dy times dy dt. Okay, so I'm going to get s times, now let's see if we can simplify this a little bit. Dx dt is s, so I'm going to get s d squared z dx squared plus, and then dy dt is s e to the st. Let's see, this is going to be d squared z dy dx. That's plus s squared e to the st dz dy, then plus s e to the st. Now we have let's see, d dx of dz dy times dx dt. So dx dt is s times, let's see, d squared z dx dy plus, and then dy dt is s e to the st, and then we have d squared z dy squared. See, that ends up being quite a long and complicated expression for my second derivative. Okay, I'm going to see if I can clean this up just a little bit. Let's see. I'm going to put the s squared e to the st dz dy out front. And then I'm going to, let's see, I'm going to have plus s squared d squared z dx squared plus s squared e to the st d squared z, we can do dy dx, okay, plus, and if you look, the next term is s squared e to the st, and then that mixed partial, and we know the mixed partials are equal, okay, so we know essentially that this term right there is going to end up equaling this term. Okay, so there are two of those. Okay, so we're going to have two of these. And then it doesn't matter whether we write dy dx or dx dy there. Okay, and then finally, I'm going to have an s squared, 2e to the st's there, multiplied together. So that's e to the 2st, and then d squared z dy squared. So you can see that taking second derivatives, in this case, can get quite complicated. Okay, so we want to do one more thing, and that is to look at the general chain rule. So the chain rule that I've presented before, x and y were my variables, and then they were functions of just a single variable t. Now we're going to let f be a function of the variables x1 through xm. So it has a function of x1 through xm. And then each of these are going to be a function of a bunch of t variables. Okay, so before I would have, say, f of x, y, and then x was a function of t and y was a function of t. But now I can imagine that x is not just a function of t. It's going to be a function of, say, t and s. And then y is going to be a function of t and s. So we're going to allow our variables x and y to be functions of possibly more than one variable. Okay, so if all of these functions have continuous first order partial derivatives, then what is df dt sub I? So I just want to figure out what is the derivative of f with respect to one of those t variables. Okay, well, it's going to be partial f with respect to x1, that first variable, times dx1 dt1. Notice that's a partial derivative because now x1 is a function of several variables. Okay, so it looks kind of the same. So then we have df dx2 times dx2 with the with respect to, say, ti. I think I wrote a 1 here, but I meant it I, because we're taking the derivative with respect to ti. And then we're going to keep going till we get df dxn times the derivative xn with respect to xi. And so this is the most general expression for the chain rule. So now I'm going to look at an example. We're going to have that f is a function of x, y, s, and t. And these are going to be interesting because x and y, those are going to be dependent on something. But s and t are going to be independent variables. So x is a function of s and t, and y is a function of s and t. But f could also be a function of s and t. So f is a function of x, which is a function of s and t, a function of y, which is a function of x and t, and then f is also just a function of s and t itself. Whew. So the question is what is the derivative of f with respect to s? Okay, so the derivative of f with respect to s is going to be, let's see, it would be df dx times dx ds plus df dy times dy ds. Okay, that's all still the same, times df ds, and then you would think about it as being times, well, ds ds. Okay, but ds ds, that's just going to be 1. Okay, so we can essentially eliminate that. Okay, and then this would be plus the derivative of f with respect to t, and then it would be times dt ds. But those are independent. T does not depend on s. So in fact, that would be 0. So just kind of rewriting this, it's going to be df dx times dx ds plus df dy times dy ds plus df ds. And that is the partial derivative of f with respect to s. Now, if I want the partial derivative of f with respect to t, well, that would be df dt times dx dt plus df dy times dy dt. And then finally, we would have df dt with dt ds, but dt ds is going to be 0. So we just have df dt. And so this is the most general expression for the chain rule and how you can take derivatives of that function f, which is a function of a mixture of dependent and independent variables.